everyone. Welcome to the week 11 problem solving session of the course Fundamentals of Micro and Nanofabrication. I am Udiptya, PMRF scholar from IIT Madras. So this time we will be focusing on two broad topics, essentially the topics of chemical mechanical polishing. So the first two videos are on them. So how we get planar surfaces, how we make planar surfaces on our wafers. We will see the first video is a kind of a theoretical overview or theoretical primer of how chemical mechanical polishing works. Second video is mostly on the technical stuffs and the tools and the processes that is involved in chemical mechanical polishing and the pipeline the wafer goes through for the polishing applications. The next half is on design for manufacturability. So it kind of addresses the gap that is between design of a device and and its manufacturability. So how to make a manufacturable design, that's what we see in these three videos. So it's design of a design for manufacturability 1, 2, and the last one is a case study. So we will directly go to the questions then, and if any doubts you can ask in the chat box, and also answer the questions accordingly on the chat box. So most of the questions are multiple choice questions, or some may be like true and false, fill in the blanks, or short answers also. Okay. So first question is from chemical mechanical polishing. Some of the process. The chemical mechanical polishing involves some processes. Okay, so you have to tell, three processes are given here, like local planarization, smoothing, global planarization. So you have to arrange them in order of their happening. Chronologically, you have to arrange them. So you have to place which one takes place first, and then the next, and then the next. So it's kind of like that. Okay, we will solve the question then. Yeah. So, assuming you have a pattern like this, okay. This is the plain one. So you are putting a conformal coating over it. Okay. This is the conformal coating. Conformal means this distance h is always everywhere it is h only. Okay. These all distances are same. So coated, and now we have to now we want to polish it. So the first thing it goes when we start with chemical mechanical polishing is that they get, so this is the pattern. So what happens is that they get smoothened. So this is this pattern, smoothening. Okay. And after some time what happens is that this gets planar. Okay, so basically this region is plane and this region is also plane, but this is some region that is not plane. Okay, so these planes are now not enough, so distance is there, and then we polish it for some more time, so we get this fully plane. So this is local planarization, and this is globally it is planarizing. So essentially the first would be local smoothening, local planarization, and global planarization. That will be the flow. Okay, let's go to the next one then. Any doubts you can ask. Okay. So in chemical mechanical polishing, we have to tell the polishing pad is rejuvenated by. So these are 4 options, so you have to tell which one of them is correct. We'll go to the answer then. So here we can see the diagram of a chemical mechanical polishing equipment. So you can see all the elements here. So essentially the polishing head is this one, that is used to give the force and hold the wafer pinned to the pad. Slurry is this one. Okay, you can see slurry, conditioning head, and the platen. So you can see from the here what are the uses here. So you can see that the uh, the polishing head is basically pinning the wafer to the surf pad, and the platen is something that is holding the pad and it's rotating it. Slurry is abrasive, and the conditioning head is something that it also referred as pad conditioner, is something that has some diamond teeth on its one side, and that is like basically these teeth touch the polishing pad. So what happens is that any the whatever is polished, it gets accumulated on the polishing pad, and its polishing abilities decrease as it gets because of this whatever things are removed, they get settled, and the pores that are present on the polishing pad, they get smoothened up, just like how it happens for sandpapers. So this pad conditioner is something that it has this diamond spikes. What happens is that when it's rotating, they remove this like deposited materials, and then the pad is good to go for another round of like good to go for polishing. So that's the purpose. So here the conditioning head is something, or the pad conditioner is something that is rejuvenating the polishing pad. Okay, we will go to the next question then. If any doubts, you can ask. Okay. So this is a fill in the blanks kind of question. So the statement reads that in chemical mechanical polishing, dash typically happens when we have a density variation. So the density variation would result in aggressive removal of material in some places and sparse removal in other places. So you have to identify which one of the following happens because of density variation, and this density variation results in aggressive removal. So basically, in some places it is aggressively removed, and in some places it's sparsely removed. So here we can see as an example, uh, here we see that here this oxide is there, so basically silicon oxide, and we have this tungsten plugs. So here we have a difference of tungsten plugs. So we see that whenever there is a like this tungsten plugs tends to polish, their rate of polishing is higher. So what happens is that as there are more plugs here, this region is polished at a higher rate than this portion. So you can see that there is aggressive removal here, while the removal here is very sparse. So essentially erosion would be the correct one. So another thing is dishing. With dishing, it happens is that the, the the portion rounds off. Okay. So these are the one like dishing and erosion are some of the factors that happen usually. Okay. So this is the problem 4. We say that like different. We have to tell which the following like you have batch to batch wafers you want to manufacture, so you have to tell which are the variations that can happen in this spatial, temporal, or both. Okay, here we will see what is a batch. Basically, batch is something a group of wafers is we call it as batch. So you want to make a similar, like same design in a lot of wafers. We tell it as batch to batch fabrication. So what happens is that suppose we have a single wafer, yeah, and so basically here we have a die, here we have a die. So they are spatially like at different places, yeah. Spatially means uh, at different positions, okay, in different space. So essentially here there can be a variation, and in this there can be variation depending on the position they are at, okay. And also, like you are, as you are processing a lot of wafers, all it is not a case that all the wafers will be processed together, yeah. Um, some wafers can be processed earlier, and some wafers can be processed at a later duration. So depending on it, there is a factor, time factors coming into play. So basically temporal is something. So basically other wafers would be like processed after that. So so variations can come with time also. So basically variations can here in batch to batch wafers, variations can be spatial and temporal. So here we will have to take both. So both the possibilities of variations are possible in the case of batch to batch wafers. And a single, so in a single wafer, only spatial would be uh, spatial spatial variations would be there. Okay. So here this is problem 5. So while in a design flow, we have to tell that there are some rule checks, yeah. So you have to tell that design rule check is one checkpoint that is done before lithography rule check. So it's a statement, okay, that design rule check is done before lithography rule check. So you have to tell true or false. So here we can see that uh, the flow of the design flow basically, yeah. So here we start with the design and then we come down to the design rule check, which basically is something that so typically think that you have established those you have in your fabrication system 130 nanometer node technology, yeah. So but so essentially if you have designs that are less than 130 nanometer, so that is something that would be a faulty design, yeah, and not actually not feasible in your fabrication system. So essentially you have to so this step it will fail and it will so you have to change your designs. So when we come down to this, we reach this lithography check. So before that, we go to layout versus schematic, which means that we compare, we check that all the connections and all circuits are correct, and then we go to optical proximity correction. So it usually means some projection simulations to see the optics, like how the lithography. So it is a lithographic simulation, and with lithography rule check, it is basically how we get the data on the mask, how the masks should be prepared to get a desired pattern. So this is the lithography rule check. So essentially it comes after the design rule check. So essentially it will be true. Okay. So here, so you have to tell that random yield loss is due to. So yield is something that means that how many basically the how many what would be the success of a system, yeah. But the loss in it, so random yield loss, you have to tell that there are three like these are three reasons which can be probably which are causing random yield. So you have to tell which one of them causes random yield loss. So here we can see that here we have random windows. So anything, so the opposite if it will be systematic loss. So the difference essentially is that with systematic yield losses we can predict the losses. Okay, so but in a random it is random, so it's very difficult to predict the loss. So essentially, so what the three terms mean? For particle interaction, it means that so essentially, if you have two interconnects here, and some particle sits on it, essentially, whatever it sits here, so some particle can sit here and like short your devices. So such kind of things are like random. Yeah, so some things can come and uh, it can affect your circuit. And in other times, if you have a circuit like this and you interconnect like this, so essentially the particle may be here, so essentially it will not affect your circuit. So such things can happen and it is completely random. So essentially it will be the correct one. We will also see the other options. Performance interaction means so basically whatever intended performance or application it is supposed to do, it is not if it is not able to do. So it can be like the resistance what it has to it has to provide, the sequence, the timing, and such things. If it is not providing, this is a performance issue. Process interaction means that so typically a wafer goes through a lot of processes. Yeah, so if you consider that plasma is we also interact for deposition we have used plasma. Essentially, if you have plasma, we can see that example that plasma, most of the plasma is formed in the center of the thing. So basically, if it is the substrate, so essentially most of the deposition will happen in the center part. Okay, and in the sides it will be less. So essentially this is the part where that is most usable. So we can see that basically so we are getting some losses here. So essentially this is quantifiable. Yeah, we can quantify this loss because of the loss from the plasma side. So we can quantify this. So essentially this is something it is a systematic yield loss. Essentially only particle interaction is something that is randomly, that randomly loses the yield. So this is problem 7, and we have to tell which of the following comprises a restricted design rules for microfabrication process. essentially, if you see that these restricted design rules are made to have the highest yield. So essentially, the designer has to design. So they are so they get some considerations that you have to design such that it gets the highest yield. So with the highest yield, it means that you have to provide higher devices from us, from a smaller. So basically, if you wafer, uh, you have to get the highest. So you have to use the whole. You have to use the surface area through most of it. So essentially, so here the first option is it area penalty. So here the area penalty is a correct one because area is something that is very less here, and you have to be very particular with the area you are using, because more area you use, you lose the yield. Simple scaling. So simple scaling is something. Restricted design rules, complex scaling rules come up because here we have to adjust the uh, design such that it involves very less area, so it will not be correct. And the C option, that is litho friendly layout. So litho friendly layout is something that is kind of you can design anything, but something that is friendly to the lithographic system you have, or something that is manufacturable is also is the paramount. Yeah, otherwise the design can't reach the realization stage. So litho friendly layout is also correct option. Okay, so these two will be the correct ones. So it is a multiple choice question here. Okay. So problem 8. So so actually this polishing rate or the polishing rate or we can also so the polishing rate we can also tell it as MRR or material removal rate. So this material removal rate or the polishing rate is proportional to the pressure applied. So this pressure is applied by the polishing head, as we had seen in the first question, and the relative velocity. So P and V are something that is proportional, and so basically and when we get to the formula, it's actually K into P into V by the time that has elapsed for the polish. So essentially this P is, they called it Preston coefficient, and this is a Preston model of MRR. Okay, so essentially these two are the controlling parameters, polishing parameters that can be controlled. So this is the last question, that essentially the die sizes. So essentially we have a wafer and we have dies here. Essentially this is 1 die, 2 die, 3 die, 4, 5, 6. So these are the dies. So if we increase or decrease the size of the die, how the so you have to tell how the die to die variability will change, and the defects, how the defects will be there. So you have to tell how it will affect it. Let's see. So essentially so consider these are the two dies, two wafers. Yeah, so if we have essentially bigger dies, so okay, so these dies are dies are bigger, so essentially you have 1 or 2. So essentially if you have defect at this position and defect at this position, so so this will be here and here. So essentially we are keeping the defect density same. Okay, so you will see that here the die number 2, 3, 4, 5 are okay, but here essentially if there are as there are only two dies with the same defect densities, both the devices are not okay to be used. So essentially if you decrease die sizes, there is decrease in defect. So here it is defect is decreases, so most of the items and the yield will be higher. Okay, and but what are the things is that now as there are a lot number of dies here, they are specially at different positions, yeah, that we discussed was special variations. But here as they are spatially in a similar position, kind of they are together, the the variations will be lesser in the bigger die size, bigger size dies. Okay, and so essentially the die to die variability will be high in the uh, smaller sized dies. Okay, so that's all for today, and we'll close the session now, and thanks all for joining. We will meet again in the next week, or with the last problem solving session for this course. Thanks everyone, and you are free to leave.